Welcome to this video lecture. In this lecture, we are discussing about the measurement of unknown capacitance and the dissipation factor or the loss angle of a capacitor. A capacitor in its pure form, if you're going to use in a circuit, then there is a perfect 90-degree phase shift between the current and voltage. 90-degree phase shift between current and voltage if you're going to use a perfect capacitor. A perfect capacitor. So all the practical capacitors are imperfect. The reason is the presence of some loss in the capacitor, or that particular loss that can be represented by means of a series combination of a capacitor and a pure capacitance here. So the C here indicated the pure capacitance and R indicate what this is the inherent resistance or inherent loss or the loss which is part of this particular capacitor. So this combination will make you what you call a practical capacitance. Practical capacitance or a capacitor. So if you try to look at the phase diagram, resistive component is normally, if you are going to consider as reference, then the capacitive reactance will have a phase shift of 90-degree, and the vector sum of these two things will give you the Z component here or the impedance component. The angle between R and phi is called the power factor angle. Phi, this is basically called as the PF angle or the power factor angle. And 90 minus power factor angle. 90 minus power factor angle means what? This part. That indicates del, and the amount tan del, if you're going to calculate, then we'll have the opposite side by the adjacent side. By the adjacent side, what we'll get? We'll get R divided by XC. So this will give you R divided by 1 by omega C, and that is going to be omega RC. So tan del is equal to omega RC. This tan del indicate that this is basically a loss component. As we have mentioned earlier, that for an ideal capacitor or for a pure capacitor, for an ideal capacitor, this angle, I mean the phase shift between resistance and the reactive component has to be 90-degree. Because of the loss component, we will have some difference in this value, or I would say that the del indicate what? The amount which we lost. The amount which we lost because of the resistive component. And this component is normally called dissipation factor. So dissipation factor is nothing but tan del. Dissipation factor. The tan del is also called dissipation factor. So for a pure capacitor or a capacitance which is ideal capacitor, the dissipation factor is equal to 0, which means that there is no loss in the capacitor. So here, now we'll be looking at the measurement of unknown capacitance. So for this purpose, we are using a bridge called Shearing bridge. Shearing bridge also belongs to the category of AC bridge, which is powered by AC. and also consisting of 4 arms. So let us look at what are the different elements of this particular bridge. The first element consisting of R1 and C1. This is the unknown resistance and unknown capacitance whose value is to be measured. And we have a standard capacitor here, which is indicated by C2. We have a resistor in the third arm, which is R3, and a parallel combination of variable resistor, standard variable resistor, and standard variable capacitance on the third arm, which are indicated by C4 and R4. As usual, we are connecting the detector between these two, and we are going to power circuit by AC source. We are just going to mark the nodes as A, B, C, and D. Also, just for your convenience, we are going to mark each segment as this is Z1, this is Z3, here is Z4, and here is Z2. As we have discussed in the previous Maxwell's bridge, at balance condition, how to achieve the balance condition, already we said, we have to adjust the variable components until we'll get null reading from the galvanometer. So at balance, the product of the impedance in the opposite arms are equal, which means Z1, Z4 is equal to Z2, Z3. So let us try to find out the value of Z1 first. So Z1 is equal to R1, and we have C1. C1, the reactance become minus J XC1. Minus J XC1. Minus means there is a phase shift. We are using XC1. And this can be further simplified as R1 minus J divided by omega C1. This can be also be simplified as R1 plus, if you go into multiply and divide this equation by J and J into J is going to be minus 1. So that minus makes it plus. So you will get 1 divided by J omega C1. So the equation we are getting now is supposed to be 1, which is equal to R1. R1 plus 1 divided by J omega C1. If you want, we can also simplify the equation. We can further simplify the equation. We'll get this equation J omega C1 R1 plus 1 over J omega C1. This is going to be equation number 1. And Z4, if you look at Z4, it's a parallel combination of resistance R4 and capacitance C4. So as we know that the parallel resistance, equivalent of parallel resistance can be calculated by the equation RP is equal to R1 R2 divided by R1 plus R2. This is the fundamental law. R1 and R2 are the individual resistances. So in our case, we have two resistors, resistor and capacitor R4. So which means R4 comes in parallel with minus JXE4. So if you simplify this, substitute the corresponding value, we'll get R1 into 1 divided by J omega C4 divided by R4 plus 1 by J omega C4. This can be further simplified as R4 divided by J omega C4 going to be divided by, if you make the LCM the denominator common, we will get the equation like this. These two terms get cancelled, and we'll find the corresponding answer for Z4, R4 divided by 1 plus j omega C4 R4. So this is going to be second equation. And if you look at the third part, which is Z3, Z3 is simply R3, and Z4 is minus JXE4, minus JXE4, sorry, JXE2, minus JXE2. This can also be written as 1 divided by J omega C2. This is going to be fourth equation. Now we can apply the rule Z1 Z4 is equal to Z2 Z3. So what do we have? Z1 J omega C1 R1 plus 1, J omega C1 R1 plus 1 divided by J omega C1 R1, J omega C1 divided by J omega C1. This is first term. This has to be multiplied by, this has to be multiplied by Z4. The Z4 value we got, this is Z4, which is number 2. So we have R4 divided by 1 plus J omega C4 R4. That is equal to Z2 Z3. So Z2 I think I made a mistake here. This is supposed to be Z2. This is Z2 here. So if we calculate Z2 Z3, which is R3 divided by J omega C2. R3 divided by J omega C2. Now, if you try to simplify these two, so when the bridges balance conditions, we can apply the rule Z1 Z4 is equal to Z2 Z3. Okay, so we found Z1 is equal to this particular equation number 1. So that is, we substitute for Z1, and Z4 we got it R4 divided by 1 plus J omega C4 R4, and Z2 is only a capacitor, which is 1 by J omega C2, and Z3 is R3. So if we substitute this particular equation, four equations, Z1, Z4, Z2, Z3, we'll find the balanced conditions like this. This equation is required to simplify further. Okay, so if we try to simplify this function, we will get the result. So this part we are going to multiply here, then this part is going to multiply here. We'll also try to multiply here, and we'll find the following equation. So J omega C1 R1 into R4 plus R4. The whole thing is going to be divided by, when you talk about the denominator, first term we have to multiply with 1. So we'll get J omega C1. If you multiply this term, we'll get J omega C1. Then we multiply this with this. Here be careful, we have a J term here, we have a J term here. So as we have mentioned already, J value of J is equal to minus root minus 1. So if you're going to multiply J times J, it is going to be minus 1. It is an important relation that you should remember. So J times J is equal to root of minus 1. All right, so what you're going to get in this case, J into J become minus 1. Then we have omega square, we have C1, we have C4, and we have R4 as well. That is equal to the RHS is going to be, right hand side, R3 divided by J omega C2. Next step is we can just cross multiply and simplify further. If you cross multiply like this and cross multiply like this. So we cross multiply this term with this. Again, we have a J term. So that J into J make minus. So you have minus. Omega and omega is going to be omega square. We have C1, we have C2, we have R1, we have R4. Plus, if you expand, if you multiply R4 with J omega C2, we'll get omega J omega C2 R4. That is equal to, now this part we have to multiply with this. That will give you J omega C1 into R3 minus omega square C1, C4, R3, and R4. Again, this equation we need to separate. We have to find out the or group the terms. The real term and imaginary term. You can find this is a real term. This is also going to be a real term with including the minus sign. It's a real term. So what you can find, minus omega square C1, C2, R1, R4, that is equal to minus omega square C1, C4, R3, and R4. So some of the common terms are omega C1 is got cancelled. Then we end up with the following. We can find out R1, which is the unknown resistance, R1, that is equal to C4 R3 divided by C2. This we got it when we match the real terms on both sides. Now we'll look at the imaginary terms on both sides. So if you look at the imaginary terms, we have J omega R2 C4, that is equal to J omega C1 into R3. Here also J omega get cancelled. Then the unknown value is C1, that is calculated by the equation C2 R4 divided by R3. So this is the C1 value. So what you can see from this particular equation, that the equations for R1 and C1, they are independent. See, R1 is calculated based on the C4, C2, and R3. C1 is calculated based on the equation C2, R4, and R3. Now let us try to draw the vector diagram or the phasor diagram for the shearing bridge. So the first point, we try to find what will be V1. So V1 is nothing but the I1 multiplied by the combination of resistance and capacitive reactance. So the voltage across the resistor is going to be in phase component. That can be marked as follows. So the in phase component is going to be this, which we can assume that this is equal to I1 multiplied by R1. Now, the current through the capacitor, the drop across the capacitor, that can be marked. That is normally say reactive component, and that takes 90 degree from this. So this we can mark as I1 into XU1. So the resultant current, which we can get it by finding the vector sum of these two currents here. So this is what the resultant voltage across this particular branch, that is supposed to be V1. So V1 is nothing but the vector sum of the voltage drop across the R1, which is this, and the voltage drop across C1 alone, which is 90 degree, from the reference axis. So we have I1 R1 along the x-axis and I1 into X1 along the negative y-axis, and the vector sum will give you V1. So this particular part we already calculated. Then the next part is we have to find out the drop across R3, which is nothing but I1 into R3. So I1 into R3 is again an in phase component because the drop across R3 is in phase with I. So let us assume that this particular current is this I1 into R3. So I1 into R3 is nothing but V3. Okay, now we have to find out vector sum of V1 and V3 to get the equivalent value, I mean the supply voltage V. So as you can see in the diagram, if we add V1 and V3 vectorially, we'll get the input voltage V. So we have V3, this part indicate the V3 and this part indicate V1. We have to add these two things, then we will get V1 and V3 we are going to add vectorially. So we'll get the resultant voltage, that is the applied voltage. So I'm trying to draw a line which is parallel to this and draw a line which is also parallel to this. So this is parallel to this. Then we are going to make a diagonal here. And this resultant indicate the applied voltage, which is V. So we have already explained how to get the vector or the phasor diagram for the Shearing bridge. Now the only part which is missing is the dissipation factor. Already we have mentioned for a pure capacitor, the phase angle for a pure capacitor, the phase angle between the current and voltage is 90 degree. But because of the leakage or because of the resistive part, always the phase angle is less than 90 degree. And the difference of the resultant angle, I mean 90 minus this difference, okay, 90 minus the power factor angle, that is called the loss angle. This is what we discussed before. So this is the reactive component. This is the active component. Ideal case will have 90 degree, but practically speaking, you will have some kind of difference here, okay, in terms of the angle actually. So this is basically the power factor angle because this is R and this is the axis, and this part indicate 90 minus phi, and this 90 minus phi indicate that this is the loss or the dissipation. So this dissipation angle is given by 90 minus phi. Simply we can mention it by a term called del, and the corresponding angle tan del, that tan del is the dissipation factor, and this can be obtained by tan del is equal to, as we have calculated earlier, tan del is equal to omega RC here. So we can say that for a dissipation factor, equation is equal to omega R and C, where in our case we have R1, we have an equation C4 R3 divided by C2, C4 R3 divided by C2, C4 R3 divided by C2. This is for R. In our case, supposed to be tan del is equal to omega R1 and C1 for this particular case. So we already substituted the value of R1. Now we have to also substitute the value of C1. C1 is equal to C2 R4 by R3. C2 R4 over R3. So this get cancelled, this get cancelled. We are getting the answer omega C4 R4. That is the dissipation factor. So to summarize, in this particular video, we discussed about measurement of unknown capacitance using Shearing bridge. And the Shearing bridge, again, it's a 4-arm bridge consisting of 4 branches. And we have marked these branches as Z1, Z2, Z3, and Z4. Z1 consisting of series combination of R1 and C1. Z2 consisting of a capacitor. Z3 is a resistor, and Z4 consisting of parallel combination of variable resistance and capacitance. Now, when the bridge is balanced, the product of resistance or the impedances, the opposite arms can be equated. So we'll have the equation Z1, Z4 is equal to Z2, Z3. And we will have 4 terms, one for each Z, Z1, Z2, Z3, and Z4. We substitute, we simplify, and we separate the real term and imaginary terms. From the real term, we found the value of R1. From the imaginary term, we found the value of C1. Then we also draw the Phasor diagram. We know how to draw the Phasor diagram. And then we have calculated the dissipation factor. Dissipation factor is for this particular circuit is going to be omega C4 into R4. Hope this lecture is beneficial. Thank you for watching this lecture.